There's a puzzle I'd like to show you. It has to do with being tired. Everybody knows about being tired. Your doctor asks sensible questions. Are you sleeping? How's your thyroid? What are you eating? These are fine questions. But they miss something. Because there is a muscle inside your eye, so small you could fit it on the head of a match, and that muscle, on any ordinary afternoon, is probably doing a good fraction of the work of making you feel dead by 4 o'clock. And nobody ever told you about it. Look, let me just show you. Do this with me. Close your left eye. With your right, look at something across the room. A doorway, the far wall. Hold the gaze for 3 seconds. Now drop your focus to your thumb, held 6 inches from your face. You felt it. A little click, a tiny pull, a subtle pressure just behind the bone of the eye socket. That was a muscle moving. I want to tell you about that muscle, because it is one of the most beautiful pieces of engineering in the human body, and because the story of what it does to you turns out to be a detective story, and the culprit is not who your doctor told you it was. I got interested in this, by the way, because I kept noticing something. People I knew, intelligent people, reasonable people, would finish their workday feeling absolutely wiped out, and they would all describe it the same way. I'm fried. My brain is mush. I can't think anymore. And I started to wonder whether that phrase, I can't think, was really the right description of what was happening to them. Because when you looked at what they had actually been doing for 8 hours, it was not hard intellectual work most of the time. It was staring. Staring at a screen at a fixed distance, an arm's length away. Not thinking, looking. And that seemed to me worth investigating. The muscle is called the ciliary muscle. The name comes from the Latin word for eyelash, because the first anatomists to look at it under a microscope back in the 1800s thought the fibers looked like little hairs radiating outward from the lens. Here's where it lives. Reach up and press gently on your closed eyelid. You're pressing on the cornea, the curved window at the front of the eye. Behind the cornea is the iris, the colored ring that gives your eye its shade. Behind the iris is the lens. And wrapped around the lens, like a donut around a marble, is a ring of tissue called the ciliary body. The muscle lives inside that donut. It has 3 groups of fibers, an outer layer running lengthwise like the grain of wood, called the longitudinal fibers, a middle layer spreading out like the spokes of a bicycle wheel, called the radial fibers, and an inner layer running in a circle, like the drawstring at the top of a canvas bag, called the circular fibers. All 3 layers do the same job. When they contract, they pull the ciliary body forward and inward. And when they do that, a set of transparent threads called the zonular fibers goes slack. These threads suspend the lens like the springs on a trampoline. When they loosen, the lens, which is elastic and wants to be round, springs into a rounder shape. A rounder lens bends light more sharply. The close thing comes into focus. That is accommodation. It isn't a thought. It's a piece of mechanical engineering. A muscle contracts. Threads go slack. A lens changes shape. Light bends. Here's what I find marvelous about it. You do this between 100,000 and 150,000 times in an ordinary day. Every time your eyes shift from the screen to the person across the table, from the steering wheel to the road sign, from the menu to your friend's face, the muscle fires, the lens reshapes, the world snaps into focus. You never notice the work. That, as I'm about to show you, is the beginning of the problem. The physics of this system was worked out by a man named Hermann von Helmholtz. Helmholtz lived in the 19th century, and he was one of these people who could do just about everything. He discovered the conservation of energy. He built the ophthalmoscope, the little handheld instrument your eye doctor still uses to look at the back of your eye. And in 1855, he published his theory of accommodation in a book called The Handbook of Physiological Optics. Now think about what that must have been like. Helmholtz could not see inside a living human eye the way we can today. He could not measure the tension in a zonular fiber. So he did what a physicist does. He combined his own careful optical measurements of the eye's focusing power with what he could see in cadavers under a microscope, and he reasoned his way through. The lens is passive and elastic. The muscle is the active part. When the muscle contracts, the lens curves. When the muscle relaxes, the lens flattens. That model from 1855 has survived 170 years of scrutiny and imaging and experiment. It is essentially correct. I want to stop on that for a moment, because it is worth noticing what Helmholtz did. He did not wait for the right tool to arrive before asking the question. He built his tool, the ophthalmoscope, and then he used it, and then he reasoned beyond it with geometry and physics. The answer he got, working in a laboratory that by modern standards was almost primitive, has not been overturned in 170 years. This is what a good theory looks like. Simple, mechanical, predictive, stubborn. How much focal power can this system produce? A researcher named Adrian Glasser, who spent much of his career at the University of Houston, measured this carefully in human and monkey eyes. A young eye can change its refractive power by up to 15 diopters. 15 diopters means you can shift your focus from infinity to about 6.5 centimeters in front of your nose. That's the range at age 20. By the time you are 40, that range has shrunk to maybe 4 diopters. By 60, it is under 1. The lens itself has stiffened. Its fibers have become less pliable with age. But here's the thing. The ciliary muscle does not know the lens has stiffened. It keeps contracting. 100,000 times a day, it tries just as hard as it did when you were 20. And when the lens refuses to respond, the muscle tries harder. It contracts deeper. It holds the contraction longer. Now, if you held a coffee cup at arm's length for 8 hours, your arm would burn and shake. Your biceps would complain loudly. But the ciliary muscle is made of smooth muscle, not the skeletal muscle of your biceps, and smooth muscle does not burn or shake. It just runs down its energy reserves, quietly, without telling you. Picture that arm holding that coffee cup. Now put it behind your eye. The ciliary muscle doesn't fire alone. It has 2 close relatives, and the 3 of them work together. When you shift your focus to something near, 3 things happen at once. The ciliary muscle contracts. The medial rectus muscles, on the inner side of each eyeball, pull both eyes inward toward the nose. That's why you can go cross-eyed looking at your finger. And the sphincter muscle in your iris tightens, making your pupil smaller. Physiologists have a single name for all 3. They call it the near triad. All 3 are driven by the same cluster of cells in your brainstem. It's called the Edinger-Westphal nucleus, named after 2 German physicians who described it in the 1880s. From that nucleus, a set of parasympathetic nerve fibers runs out through the 3rd cranial nerve, the oculomotor nerve, and down to the eye. The fibers pass through a little relay station behind the eyeball called the ciliary ganglion. Then they split. One branch reaches the ciliary muscle, the other reaches the iris sphincter. Same nucleus, same nerve, same neurotransmitter, which is acetylcholine. One signal, 3 muscles loaded at the same time. You can watch 2/3 of this happening yourself, right now, in a mirror. Look at yourself straight on. Now lift a finger up close to your nose and stare at it. Watch your eyes in the reflection, or have somebody else watch for you. You'll see your eyes cross inward. You'll see your pupils shrink. What you can't see is the 3rd member of the triad, the ciliary muscle inside each eye contracting at exactly the same moment. The 3 act together. They cannot act separately. The brainstem that drives them doesn't have a knob to turn off just one. Now consider what this means for an ordinary person. When you look at your phone for 8 hours, you are holding 3 muscles in sustained contraction. Not pulsing, sustained. All of them driven by the same small cluster of neurons in your midbrain. And that cluster of neurons has a neighbor. I want to tell you about that neighbor, because it is where the detective story takes its first real turn. Deep in your brainstem, on each side of a little cavity called the 4th ventricle, sits a tiny patch of cells. Each patch is about the size of a match head. Each one contains roughly 15,000 neurons. The cells are faintly blue under a microscope because of a pigment inside them. The whole thing is called the locus coeruleus, which is just Latin for the blue place. Now, this little blue place is where most of the norepinephrine in your brain comes from. Norepinephrine is the chemical of alertness. It's the reason you wake up. It's the reason your attention jumps to a slamming door. From the locus coeruleus, projections fan out to nearly every part of your brain. Your cortex, your thalamus, your hippocampus, and, here's the connection I want you to notice, the Edinger-Westphal nucleus, the one controlling your ciliary muscle and your pupil. The two structures are wired together. In 2005, two neuroscientists at the University of Pennsylvania, Gary Aston Jones and Jonathan Cohen, published a big review paper in the Annual Review of Neuroscience. They laid out a theory of how the locus coeruleus works. They said it has two modes: a steady background rate of firing, which scales with your general level of wakefulness, and short bursts, triggered by salient events. And here is what they found. This is the part that ties everything together. The steady background firing rate of the locus coeruleus is directly correlated with the size of your pupil. Not a metaphor, a mechanical correlation. When the locus coeruleus is firing fast, your pupil is large. When it is firing slowly, your pupil is small. Your pupil is a gauge. It shows what your arousal system is doing moment to moment from the outside of your face. Now, what happens when you get tired? The tonic firing rate of the locus coeruleus drops. The sympathetic drive to the pupil weakens. The Edinger-Westphal nucleus, without a steady input from above, begins to fluctuate, and your pupil starts to oscillate, slow waves of constriction and dilation in complete darkness, for no optical reason. Two researchers in Germany, Helmut Wilhelm and Holger Lütke at the University Eye Clinic in Tübingen, figured out how to turn this into a test. They called it the Pupillographic Sleepiness Test. They published it in the journal Sleep in 1998. You sit in a pitch-dark room for 11 minutes. An infrared camera watches your pupil. They compute something called the pupillary unrest index. And, this is the part I find genuinely striking, the result predicts microsleeps on an electroencephalogram with high accuracy. Your pupil, while you sit quietly, is telling on you. And while your pupil is telling on you, something finer is happening in the ciliary muscle, in the same eye. The ciliary muscle, when it's under load, develops its own tiny oscillations. They're called accommodative microfluctuations. They're too small and too fast to see, but you can measure them with an instrument called an infrared optometer. They come in two flavors: a slow component at about 0.1 to 0.6 Hertz, which seems to be feedback corrections, and a fast component at about 1 to 2.5 Hertz, which is partly driven by the pulse of the blood in the ciliary body itself. In a rested eye looking at a distant target, the fast component is small, low amplitude. The muscle is really at rest. In a fatigued eye looking at the same distant target, the fast component is larger, more amplitude, more power. A Japanese research group, Kajita, Ono, Suzuki, and Kato, measured this in subjects with asthenopia, which is the medical term for eye strain. The word is Greek. It means weakness of sight. They found that the asthenopic subjects had elevated microfluctuation power even when they were looking at things far away, when the muscle should have been fully relaxed. The muscle wasn't relaxing. It was holding a low-grade residual contraction, an invisible clench. So here's the picture. It's 4 in the afternoon. You've been at a screen. Your ciliary muscle has been under sustained contraction for hours. Your iris sphincter has been contracting in sync. Your medial rectus muscles have been pulling your eyes inward, all of them driven by one tiny nucleus in your midbrain, which sits next door to the blue place, whose output tells the rest of your brain whether you feel awake. The fatigued muscle sends a steady afferent signal back up through the trigeminal nerve, the big sensory nerve of the face. The signal reaches the brainstem. The brainstem responds to the load by shifting autonomic balance. Your cortisol climbs. Your attention drops. Nothing is telling you any of this in a language you recognize. Nobody is yelling inside your head. The muscle behind your eye can't speak. The Edinger-Westphal nucleus can't wave a flag. All they can do is emit signals, and those signals get integrated into the general murky business of how you feel. You experience the sum, not the parts. You feel tired. You do not feel specifically that a ring of smooth muscle has been quietly clenching since 9 in the morning. But it has. You have blamed your brain, your age, your blood sugar. You've reached for coffee. It was, in significant part, a muscle in your eye. Now, I learned a long time ago, from my father actually, to tell you exactly how certain I am of a thing. Not more, not less. Let me do that now. The mechanics of accommodation, Helmholtz's model, is as settled as physics gets. Confirmed by ultrasound. Confirmed by magnetic resonance imaging of living eyes. Confirmed by the predictable effects of drugs. Put a drop of pilocarpine in your eye and the muscle contracts. Put a drop of atropine in your eye and it relaxes. Every ophthalmologist in the world will agree on this. Trust this part completely. The locus coeruleus driving pupil size, this too is strongly established. Single-cell recordings in monkeys, replicated in humans with imaging, replicated by the Pupillographic Sleepiness Test across labs for 30 years. Trust this. The accommodative microfluctuations as a direct signature of ciliary fatigue, this is moderately established. The effect is real. The muscle clench is measurable. What's less certain is whether the microfluctuations are a cause of the tired feeling or merely a marker of it. Treat this as probable, not proven. And the last piece, that afferent traffic from a fatigued ciliary muscle contributes meaningfully to your whole body fatigue. This one is plausible, but not directly quantified in humans. The wiring is real. How much of your afternoon slump it accounts for, nobody has measured precisely. This is a guess, a physiologically consistent one, but a guess. I'm not telling you your tiredness comes entirely from a muscle in your eye. It does not. I'm telling you there is a contribution your doctor does not measure, because the instrument to measure it sits in a research lab, not in the examining room. And that contribution is free to fix, if you know where to look. Now here's something that should interest you. Pilocarpine, the drug I just mentioned, has been in medical use since the 1870s. For most of that time, its job has been to treat glaucoma. You drop it in the eye, the ciliary muscle contracts, and because the muscle is mechanically connected to the drainage sieve between the cornea and the iris, the sieve opens wider, fluid drains faster, eye pressure falls. That drug has been saving people's sight for 150 years. The drug, at the molecular level, is doing exactly what your ciliary muscle does every time you look at your thumbnail. Same receptor, the M3 muscarinic receptor. Same chemical cascade, same mechanical outcome. The only real difference is that the drug holds the muscle in contraction for 6 or 8 hours, while your own nerve pulses on and off naturally. That is why pilocarpine, when it's used more recently as an eye drop for presbyopia, causes headache and a sustained ache behind the eye. The drug is doing what your muscle already does. It's just doing it harder, without the pauses. The side effect is the signature of ciliary overwork made pharmaceutical. And then there's the other side of it. When you reach for your 3rd cup of coffee to push through the fatigue, you are chemically manipulating the very same locus coeruleus system whose output, through your pupil, is telling the truth about how tired you are. Caffeine blocks a molecule called adenosine. When adenosine is blocked, the locus coeruleus fires faster. The blue place broadcasts more norepinephrine. Your pupil dilates. Attention sharpens. You have pushed your arousal broadcaster to work harder, without addressing the muscle whose quiet clench started the whole cascade. I'll tell you something about myself. For a long time, when I was working on a problem, I would reach for coffee at around 3 in the afternoon, the way most people do. And I assumed, as most people assume, that I was reviving a tired mind, that the coffee was sharpening my thinking. It probably was, a little. But the thing I noticed once I knew about the ciliary muscle is that on days when I had been looking at a distant blackboard, or standing and pacing or teaching, the coffee was not necessary. The tiredness wasn't there. On days when I had been hunched over a page, the coffee felt essential. Same hours, same food, same sleep, different muscle loading. I do not claim this as science. I offer it as an observation worth testing on yourself. Now, I'm not going to tell you coffee is bad. Coffee is a fine drug. Pilocarpine has saved many eyes. These things exist for real reasons. What I'm telling you is that a good fraction of the fatigue you feel at 4 p.m. on an ordinary Wednesday after hours of screens is coming from a grain of rice muscle that would respond to 20 seconds of looking out the window. 20 feet away. 20 seconds. Every 20 minutes. That rule, the optometrist did not invent it to sell you anything. They invented it because a muscle, like any other muscle in the body, is not meant to be in sustained contraction all day. When I was a boy, my father used to tell me when he caught me reading with my nose in the book, look up every once in a while. Rest your eyes. Look out the window at the trees. I thought he was being a father. I did not think he was doing physiology. But look at what he was telling me. Look up. Release the ciliary muscle. Rest your eyes. Drop the tonic load on the Edinger-Westphal nucleus. Look at the trees. Give the muscle a distant target and let the zonular fibers pull the lens flat. He was doing physiology. He didn't know about muscarinic receptors or the blue place in the brainstem. He just knew that his eyes felt better when he looked at the horizon. He told me. I forgot for many years. I'm telling you now. Close your left eye again. With your right, look at something distant. The window. The far wall. 20 feet away. Hold the gaze for 20 seconds. Feel the quiet. That is a muscle letting go. So tell me, where in your day does this tiredness find you most? Most people think afternoon tiredness comes from a tired brain, a skipped meal, or not enough sleep. The anatomy says something different. There is a smooth muscle in your eye, smaller than a grain of rice, that performs well over 100,000 contractions every day, and almost nobody has told you it exists. What happens when it stops getting a break isn't something your doctor's office measures. It might be the thing you've been blaming on everything else.